flow problem. Each one of them is a network flow problem. You introduce the variables per arc, flow conservation, flow variables. Of course, there's a lot of these, but that's fine. Each one of them have a separate set. You can project the flow variables onto the original variable space. It's known that for a single diagram, this is of course a convex hull relaxation in the lifted space. Again, not so surprising, it's a network flow model. But when you have multiple of these, it's definitely not, even for two, it's not a convex hull relaxation anymore, even if the variables are in the same order. That's a polynomially solvable problem, but the two network flow problems is not a convex. The two network flows in the lifted space that you get is not a convex hull relaxation, even though you can solve it in polynomial time. But if the variables are in different orders, even if you have two diagrams, this is an NP-hard problem. If I'm getting the complexity right, we're working on the complexity now. And then even if you have the same variables and you have three, it starts to blow up. I mean, you can, it's a hard problem. So these are two different networks, or k kappa different networks, and each one you want to take consistent paths. And you want to maximize the total weights. So is that clear what the formulation is?
So this problem has been studied before? Sort of different networks, and I have constraints that these edges must have the same value? Like a consistent network flow problem? I haven't seen it.
I haven't seen it. So this is, we've kind of just, I don't think, I didn't see it in the literature, for example. And so yeah, me and these guys from Clemson, so Cole Smith that I was talking about, and also his PhD student now in Cincinnati, we're working on this problem and studying the polyhedral structure of multiple consistent paths. You can also solve this via constraint programming. So there is a notion of constraints being modeled with diagrams like these, and they try to solve it with constraint programming. It sort of works well, but not that great. It works better when you just want to solve the feasibility problem. So you have a bunch of these diagrams. You don't know even if you have a feasible solution between them, right? And so their constraint programming works okay, but once you put objectives into constraint programming, really isn't the proper way of solving a problem that you want to use MILP, because LPs are very good at dealing with objective functions.
So just a quick question. So how much do I lose if I introduce new variables for each one of these diagrams and then have constraints for equality for the corresponding vertices?
So you would have a variable saying,
so I'm going to have a variable for each diagram, different variables for each diagram, and then to enforce the consistency, I will add some equality.
Just within the constraints of the IP that you get. I guess it's probably just a reformulation of this. I think it's probably the same. I think if you project it in some way, you probably get the same. But I don't know. I don't want to say that for sure. But I think I have the idea that it's the same. But there's various things. I mean, the model itself, right? Are you just going to impose it like this? Or do you want to say that the variables from the first one equal the variables from the second one, the variables from the second one equal the, I mean, it's just easier for a solver to solve. I guess the relaxation value should be common, although I don't know. And then you want, yeah, I know. I don't know. These things we're trying to figure out. It's a great question. Okay, cool. So that's what we do. We build the diagrams, we build this thing, we get this problem here, longest path, polytopes, fine. Good. Questions so far. That's the framework. Now, the issue that we get is exactly the issue that you've been talking about, or that we've been talking about. These things blow up too big, okay? And it's not only that you can't build the diagrams individually, okay? It could be that there's plenty of memory in your computer to build each one of these. Because even 20 variables, this can be a pretty hard problem. So it could be that you can build each one of these in memory limits, and it's fine, even polynomial in size. But the ensuing IP is really hard. Okay, these are, I mean, you dump these into solvers, they take a very, very long time to solve, okay? It's a complex problem, that's all. And well, again, we're working on the polyhedral study to try to understand how to do these faster, but it's hard. So even if you can build the diagrams in polynomial space, the IP becomes too challenging. So what do? What we're gonna do is, as opposed to requiring that every single path has exactly the function evaluation, we are going to impose the restriction that every single path provides an upper bound on the objective function evaluation. If that's the case, then when I optimize over this collection of diagrams, I get a global upper bound of the entire problem. What's even better is that when I solve that problem, if all the constraints are in the IP, then I actually get a feasible solution. What it evaluates to might be different from what it actually is, but I do get a feasible solution. So now I can just plug that into the functions, and for free, get a lower bound as well. So we have an upper bounding mechanism, a lower bounding mechanism, and so you have an entire branching bound that you can set up around this. And that's the framework. So here, let's go back to our function from before, 4 variables, square root on the top. Here's my diagram. Suppose this is too big because I want a smaller diagram, all right? You might be able to compact a couple things here, I'm not sure. There is a notion in decision diagrams of a unique reduced decision diagram, but that is not in the diagrams that we're using here. These are different. So we don't know that there's a unique reduced diagram in this case. Out of the scope maybe for right now, but yeah, you don't know if this is the smallest possible thing you can do. So what we can do is, as we're building this, okay, remember we're doing this in a top-down fashion, just blowing up the states. If I get beyond my maximum allowance, suppose I say I do not want more than 4 nodes on any particular layer, I look at these 2 nodes. Now, if I were to put these 2 things together, the problem is I have to lose information. But that's fine, just like LPs, relaxed integer variables, we are going to create a discrete relaxation, eventually linear relaxation, but a discrete relaxation for each term, because I can just over-approximate what every solution is going to be. In the case of a linear function, inside a square root function, for example, what you can do is you can just merge these nodes together and change the states by taking the maximum state and evaluating it. So if I think about this, merging these 2 nodes together, they will have different state values, okay? No questions asked. But actually, when you're taking the square, you want to take the minimum one, because the smaller it is, the higher the impact on the objective function is going to be, because it's a concave function, right? But you can always figure it out, minimum or maximum, depending on the function you have. So I can kind of merge these 2 and decide which value I want to take. If I take the higher value always, I end up with a relaxation, right? Every single path now in this diagram will be at least as large as what the function actually evaluates to. At least as large. If I were to take the lower value here, so yeah, I mean, you can look at it here, right? X prime evaluates to 2.23 f of x prime. But if I take the path here, I get 2.41. That's fine. It's a relaxation. That's what I want to build, actually. This solution doesn't change because I've taken that path. And then, I mean, you can play the game with the under also, so you can build a restriction, if you will. And this is just by changing the states that you associate with the nodes. That's all. And so I can make this thing, now this is where the particular function becomes important, right? I don't know how to merge states for general functions. But that can be part of the model as well, okay? You can say, you need to give me a model where it's recursive and you tell me a relaxation operation on the states. If you give me this, then I can build the diagram as small as you want. It can be 1 if I want, as small as you want.
So the upper bound follows from the merging condition?
Yes.
So if there were some negative values, for example, inside, it might be more tricky to have the upper bound?
Yeah, but I guess if you still had this thing with the negative values for the coefficients of the variables, you could still merge the states by actually take what you, with negative values, yeah, that gets a little bit trickier, because now, you're taking a square root, so.
I mean, you have to make sure that the whole thing evaluates.
You have to make sure that it's feasible and all these things. Yes, I agree, that's a little bit trickier in this case. But if you have like if you have a squared out there, you can do certain things. There's a way to handle that, but not for a general function, right? So if you take, for example, sine on the outside of this linear function, it becomes challenging. Even if you have a linear function with all positive coefficients divided by another linear function, but a different one with positive coefficients, this also can become challenging. You can do it, okay, but the recursive model is very bad. And it's trickier than this one. This one's particularly easy when you have linear functions with some convex function outside. Okay, and then obviously, yeah, so this is going to be a restriction. Yeah, so these relaxations are built via dynamic state aggregation. If a layer exceeds its maximum size, pick 2 nodes. You can actually pick a collection of nodes, doesn't matter. Merge them together. The relaxation operation ensures that the diagrams are relaxed. In this particular paper, you can think of a submodular set function as just a binary optimization model. And so if you're maximizing your min, and then here actually for this result, we are just using this kind of binary set and saying, you can just say the state is the binary set, and then you can do various things by like either taking the intersection of the sets when you merge them or taking a union of the sets. Depending on your maximizing or minimizing a submodular or supermodular function. But that's all fine, you can do it, which is the important part. And so I can have 10 terms, some submodular, some supermodular, some linear, and it's all fine. And then this we've kind of been talking about if you have some convex or concave composition function. Really, this is just a kind of special case of it. But yeah, I mean, you can prove these things. It's not too challenging to see, actually. Yeah.
So, you said one of the cool things about this is you kind of automatically get this upper and lower bound, so you can kind of put it in there and branch it down, kind of thing. So, submodular and supermodular optimization are kind of cases where modulo some subtleties, but there's pretty good kind of Polytope approximation algorithms for a lot of these cases. So if instead of measuring kind of how many problems I solve in some amount of time, you say, if I cut off my time here, like how does the solution quality of my bounds compare to the bounds I get from an approximation algorithm? Do you have a sense of how that compares?
So are you saying that each one of the terms are all submodular, for example?
Suppose I have like one term and it's submodular.
One term, yeah. So then it becomes, you probably are going to want to opt for one of these special, even just like the algorithms that can solve it optimally, or one of these Polytope approximations, it could potentially provide a better relaxation bound than we have. But when you merge these things together, and some are supermodular, some are submodular, this is where you kind of get your advantage. Yeah, and we are trying, and this goes around maybe what you were saying before, to prove something about this relaxation. How good is the relaxation? Yeah, it's kind of hard. You can say something very coarse, but it's nothing like, when you're using one of these Polytope approximations for so much.
Do you have like an experimental sense of how good the
yeah, they're quite good, and they're better than, for example, when you dump these into Barron or Skip, and even if you reformulate the problem so that it's all convex, and so just like adding certain variables and doing various things, even our relaxation bounds can be quite better. Now, but the good and bad thing is that we control how good the relaxations are. I can build it for each term exactly, okay? And then I know I'm going to get exactly the bound, but it's going to be super hard to solve. As I decrease the parameter that's allowing me to grow the complexity of this diagram, yeah, I mean the relaxation becomes worse, but then you get the time benefit of solving it super fast. Way down, yeah, it's tough to say. All right, so yeah, I mean you can put this in some concrete mathematical framework, right? Let's assume we have maximization problems. We see that nodes are uniquely mapped to states. To merge two nodes means to associate a unique state to nodes. And you can define a relaxation operation. And you can say that, again, this is part of your model, not something that is outside of the model. This is, you have to provide this for us. You give me two states in your state space. What happens when you put them together? And you just want to, you have this kind of, this very easy condition that you just have to satisfy. What are valid relaxation operations to ensure that the lengths are correctly bounded? Depends on the function. That's why I say that it's part of the model itself. Now, when you have one of the functions that we studied in this problem, you can just use the relaxation operation we defined. But in general, you have to come up with these things. And so you look at the cost to go. So you have a state, and you think about what is the highest function evaluation you can get based on that state. If you can prove something like this, so if you take the relaxation between these two states, you can prove that the cost to go of the relaxation operation on those states that you define bounds that, and then you're fine. Pictorially, yeah, I mean, this shouldn't be too hard to see, perhaps, right? You just want to make sure that you're never going to go above the axis.
So can you automate the relaxation operation? I mean, over all possible ways of merging, there's an optimal one?
Oh, I don't know, yeah. I mean, you're saying if you have a given recursive model, and you even give me the relaxation operation, what are the best nodes to merge? I suppose is your question, right? Yeah, we use a heuristic for this. Because it's, again, it's just like proving bounds when you relax these things. It's really hard to tell. In general, if you think about it, you're going to want to opt for ones that are very close to each other. Right? Because the information I'm losing is that I'm going to be merging these states together, and I want to see the cost to go to be almost equivalent. But if you also think about the square root function, okay? If I take values that are really, really far away from 0, so very high, and I merge those two things, the difference is going to be small than if I take very small ones, right? Like 1 to 4, or 100 to 103, right? They're both a gap of 3, but that's going to be so much closer when you look at the rest of the cost to go. So the heuristic we use is to kind of minimize the difference between the cost to go and picking those things. But you also don't want to spend too much time on this, because part of the advantage is that these diagrams can be built so quickly. And if you build small ones, you can solve the IP super fast. And so we can kind of handle a search tree node very quickly. That's one of the advantages. But of course, you need to balance these things with the amount of time you spend on relaxation versus the amount of time you spend on branching. The IPs have to deal with this. Every branch about procedure kind of deals with this. But yeah, I mean, so the automation we use is the heuristic where we try to minimize the difference in the cost to go. Cool. Yeah, I mean, improve kind of some simple things, right? Take some maximum of the states if it's a convex function of a linear function, and it's going to be fine.
Not necessarily monotone?
I think it's
For a general function?
okay for, as long as it's convex, right? Because even if it was like this, still you're going to get, yeah, because then you're going to get more negative impact if you kind of go downwards. I think it should be fine even if it's negative, yeah. But let's be careful, make sure that that's true. I don't want to, sometimes when I do a presentation I say things that are absolutely wrong, but I think it's fine. Because yeah, if you just think about, even if you had here and here, right, and I was trying to merge these two states, if I were to go here, I'm starting to decrease my objective as I start to take my actions. But once I take the maximum, suppose I'm at 0 at the lowest value here, now when I'm taking it, I should be increasing my, so I think it's okay, actually. I think, but we'll check. And yeah, I especially because I think we proved this for just general submodular set functions, you can do various things. The state just becomes the actual set of variables that you've taken or not. So a huge state space, but that's okay. You can still just take the intersection and then union for relaxations. Again, depending on if you're taking minimums and maximums. That's the power. We can do both, right? And the term as long as it decomposes. Cool. All right. Getting to a good point. So as far as timing, so again, you decompose the objective function, you reformulate it as the consistent path problem, you solve the consistent path problem. If I had to relax diagrams, which we have to do every single time, because once again, even if I can store these things in memory and load the IP, it will never solve, it's too hard. So we always opt for merging. We get pretty decent bounds compared to, for example, the root node bound that Barron or Skip might give you, which are nonlinear solvers. And so, yeah, we build this thing, we solve it, we get an upper bound. If the constraints are all linear and they're imposed within the IP that you're solving, you now also get a feasible solution. This provides you the lower bounds. You are primed for a branch and bound procedure. You pick some variable, you branch on it, build the diagrams again. We build them from scratch. You could possibly implement this with modifying the diagrams you already have to provide a little bit more efficiency. We aren't doing that yet, although I think that it may help. But yeah, we throw away the diagrams every time and build new ones. We're building pretty small ones in general. I think that in the experiments, at least on this portfolio optimization problem that I'll show, I think we put the width at 16 maximally, something like that. But you're doing 50 variables, and these things would grow very, very large in general. So we're merging every layer quite a bit, but that's okay because as you get further along in the diagram, the values in the inside of the function become larger and larger, and so when you're merging it, it becomes less and less kind of a problem. But that's if you have a concave function. Totally depends. There's some problems that didn't work so well on, of course. We tried, for example, Alper has another paper where he did some project costing thing. I don't remember exactly the problem. There was an e to some linear function, but somehow he was able to solve the problem with 200 of these terms. We tried, we couldn't do it, right? So it was like e to a linear function and a set of them. And yeah, I mean, that's just orders of magnitude worse than his results. But yeah, bad recursive model, I suppose.
Oh, really? So if you have the linear function in the exponent as opposed to the basis, it makes a big difference?
For that particular problem, it did not work well. You could define this in the same framework. You can solve the problem. Right. But it was, I mean, we solved them, but like they solved instances in 0.1 seconds. It took us like 100 seconds. Maybe we weren't merging correctly. It could be we were just picking the wrong ones. Yeah, I don't know, tough to say. But yeah, that happens, of course. Yeah, so, yeah, lower bound, and then, yeah, so then you branch. What we branch on is we find the variable that's losing the most information, which can be measured in different ways, but there's a way of doing this in some kind of controlled fashion. Yeah, so this is just redefining the function. Just to show you what we tested, and then I'll conclude. We have other experiments, but I think that's enough. We have about an hour, so we're at 55 minutes. Yeah, we basically just extended the generation procedure that Alper did. Exactly the same thing, just in this new, to include these extra terms. Yeah, exactly. So we used width of 16. We're using Cplex as the solver. Actually, I wish we used Gurobi, because Gurobi is so much faster than Cplex these days. Anyway, we compared with Barron. So when we submitted the paper the first time, one of the referees were like, why don't you just create a convex reformulation so that you can assume convexity in scale, right? Or in Barron, you can actually just say that you have a convex function. They're able to exploit that and do problem-specific things. So we did. We used the formula. It's still much faster. And I showed these results. If you want to, so yeah, again, Barron's solving these amount scale. And the bounds also are much better at the end as well. If you want to see how it looks like more specifically, so they're colored. Those of you who are colorblind, they're also different dots. Those of you who can't see that, also different sizes based on n. Yeah, so you see that once they can become bigger, right? So yeah, I mean, anyway, we're solving many. A lot of these time out, we're able to solve them. And if you look at the gaps, you look at the bounds also, they're really, really much better. There are also a few instances always, whenever I've used decision diagrams, where I know that it should solve it faster, but it doesn't in some sense, and I think that's because we start branching in some very bad direction, right? I guess these software engineers at Gurobi and Cplex, they work on how they should branch all the time, and like we're just using some simple heuristic, and so there are in almost all of the papers that we've studied several instances that are just like far off, that were way, way worse, and it's just the bounds are good, it's just we're going down some path that fails, but anyway, that's the way it goes. But it's very good. Again, there's other problems that we're not so good at, but that's the way it goes. So I'll wrap up here if you guys have more results, but that basically covers it.
Okay, so there's another class coming in, so if you have a quick question.
Really gotta go, yeah.
Yeah. Otherwise, okay. So as usual, there are refreshments in 301. You can ask